Hey physics babies, welcome to Pandemic Education episode 6. Today we're going to be talking about electric potential difference, aka voltage. Let's get into it. Okay, so this is lesson 3 of unit 5, electricity and magnetism, and today we're talking about voltage. Our objective is that by the end of the day today, you will be able to determine the electric potential difference of a uniform electric field to calculate the work required to move a charge through that field. So whenever you hear electric potential difference, I need you to think of voltage. It's, just a more scientific way of putting it. You know how it goes. Something that should be a little bit familiar in here, though, is we're going to be calculating work. Instead of the work being done by us pushing or pulling something, though, or friction, we are actually going to be talking about the work that an electric field is doing to move a charge. This is a little clip. If you are interested in watching it, download the PowerPoint. It's like 3 minutes. I'm, for the sake of time, gonna skip it. It's a song. It's a cute little cartoon. If you like watching it, definitely do. Okay, so last class, we talked about the direction an electric field line flows. So remember that our electric field lines flow from positive charges towards negative charges. And remember that our field lines can never cross. They radiate outwards in all directions, not just a single direction. And because they can never cross, we end up getting these curves when we have two charges next to each other. So, for example, looking at this positive charge here to this negative charge, we've got one going straight across. And because these field lines want to point toward this negative charge, they end up curving towards it so that they actually don't crisscross each other, but still point in the direction they want to go. Similarly, with my two negative charges, we've got these nice straight lines, straight field lines coming into the particle. And then as we get closer towards the middle of the two, they begin to curve so that they don't cross each other. Over here with our positive charges, the image looks the same, but the direction that the arrows are pointing has flipped so that they are not pointing towards the charge, but are instead pointing away from that positively charged particle. So I want you to take a second, pause the video, and think about it. How can we use what we know to design a straight and uniform electric field? I want my field to be completely straight and uniform, meaning it's the same at any single point within the field. So pause the video, think about it, and when you're ready, we'll move on. Okay, so a uniform electric field occurs if we have a positively charged bar and a negatively charged bar. Remember, our field lines always point from positive to negative, and because these aren't single point charges, we've got that positive and it flows straight down to the negative. So now let's talk about our electric potential difference, or delta V. We use volts to measure this, capital V, or we can use joules per coulomb, so J over C. The electric potential difference, or delta V, is the electrical pressure that causes charges to move. It's created by a difference and separation of charge plates. We call it electric potential difference, but we also call it voltage. Both are perfectly appropriate. Know that it doesn't matter which version you're being asked for, you're asked for the same thing. So electric forces can cause movement. If our electric forces cause things to move a certain distance, what do we get? We get work. Remember, work is a force applied over a distance. So our delta V, electric potential difference, is equal to the work done on the charge divided by the charge of the particle. Take a second, copy this down into your formula sheet or into your notes so you can reference it. So work is the force, let me move that down here. The work done is also equal to force times distance, right? Just like it was before with when we were talking about like momentum and conservation of energy and all that stuff. Work has always been force times distance. So with that being said, we can change our formula. Instead of writing work, we can write the force on the test particle times the distance between the plates. And that's the distance that something would be moving from the positive towards the negative. Take a second, write this down. If you need to identify your variables, make sure you do that as well. Very similar formula, but depending on what we're given, sometimes we need to change the way that we write our formulas to be able to solve. So as another reminder, electric force divided by charge is equal to E, which is the electric field strength. So we can actually rewrite this formula another time as our electric potential difference, delta V, equals the electric field strength times the distance between our two plates. So depending on what you're given, you're going to want to pick one of these three formulas to solve for your electric potential difference. So we actually have an example. We've got a positive test charge, Q. I'm going to write this down on my notes and I'll show you in a second. We've got Q equals 1.0 times 10 to the negative 6 coulombs. It's in an electric field created by charged parallel plates that exert a force. Fe is 2.0 times 10 to the negative 4 newtons. And our plates are 5 centimeters apart. And we want the voltage. Gosh darn it. Okay, so let's look and see. Okay, so here are all of my givens written out nice and neat for us. And we want to determine our voltage. So based on my givens being Q, the force, and D, I'm going to use the formula that voltage is equal to F E times, times D over Q. So one thing we need to think about though, 5 centimeters. Remember that distance is always measured in meters. So let's take this 5 centimeters and turn it into meters. In case you've forgotten, remember King Henry died by drinking chocolate milk. Centimeters is right here, and I need to move my decimal place to get to meters. 2 spaces, 1, 2. Sorry, 2 spaces to the left. So my 5 centimeters is going to become 1, 2, 0.05 meters. So now let's take all of my givens and plug them into my formula. We're going to get 2.0 times 10 to the negative 4 times 0.05 divided by 1.0 times 10 to the negative 6. Take a second, plug it into your calculator. I will as well. Let's see. Okay. So 2.0 times 10 to the negative 4 times 0.05 divided by 1.0 times 10 to the negative 6. So this is what it's looking like as I'm getting ready to plug it in. And my answer is, oh, I made a mistake when I was typing. I didn't type 2.0 times 10 to the negative 4. I accidentally just typed a 4. So let's try that again. 2.0 times 10 to the negative 4 times 0.05 divided by 1.0 times 10 to the negative 6. All right, I typed it incorrectly this time and I got 10. So my voltage is equal to 10. But what are my units going to be? Take a second and think about it. We can either use joules per coulomb, or what's the other one? Make sure you write it down in your notes. And let's double check ourselves. 10, yep. And our other unit, in case you weren't sure, is V for volts. And we are good to go. One more thing I want you to note is that we use delta V to talk about electric potential difference, not just regular V. So that's my fault. I should have included a delta on my formula sheet. All right, so that's going to be it for today's lesson. It's going to be it. I've got practice problems posted. I'm going to highly, highly encourage you to do these practice problems. because there is a short exit ticket assessment, but then your homework for the weekend is going to be a short quiz that is going to cover lessons 1, 2, 2.5, and now this last lesson, lesson 3. So that's it. If you have any questions, feel free to shoot me an email, or we've got office hours from 2 to 3, Monday through Friday. Get your practice in and do great things. Love you lots.